Good evening, everyone. Am I audible?
Yes, sir. Good evening.
Okay, thank you.
Good evening, sir.
So, good evening. So, just let's wait for 5 minutes and after that, we will start. So, when is your exam for this course? Manish?
So it's on 27.
Okay, on 27th. Okay. Have you received about the last class, like last minute change in the schedule? Because last time only I think one student was there. No, that was only for few minutes, I think. Nobody was there. Have you received the notification that the class timing was changed last week?
Yes,
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 sir.
yes.
The notification was received.
Okay, okay. So I think you all guys were busy. Uh, so today, if you want to leave early, so just let me know because I want to hear your experience about this course. Okay. So try to attend full class, but if you want to leave early, then just let me know. Okay, so let's start. So good evening, everyone. I welcome you all to the live session number 12. So this is our last session for the course Aspen Plus Simulation Software, a basic course for beginners. The course instructor is Professor Pravir Kumar Shah from IIT Guwahati, and I'm this course TA Amit Kumar Sharma. So today we are in week 12, so this will be our last class. So I hope you will attend the whole class, and suppose if you want to leave early, just let me know because I want to hear your feedback regarding this Aspen Plus course and our live session. So as you all know that this meeting is being recorded. So the meeting link and this PPT will be shared to you from the NPTEL team. So those who are not able to attend today, they can access this video and this PPT later on. So in the week 12, Professor discussed about the plant economy and utilities. Okay, so we have gone through many models like different block operations. We have seen many case studies also, but the plant economy is also very important. So when we are doing a complete modeling, then we are using various types of fuel, various types of like heat exchanger, different kinds of heating utility, cold utility, and all. So, but we also need to evaluate the economics of that plant. Okay, because if we are changing some parameters for a plant, then that will directly affect the cost. Okay, so it's also very important because whenever a company want to set up a plant, then they will do a techno-economic study. They do a they do a complete study of the plant. So that's very important. So for this in Aspen, we have a complete system in which we can enter the cost, like different types of cost available. Okay, and based on the parameter, Aspen will give you some results. So in the class, a case study was discussed in which the task was to setting the utilities for a plant operation, to setting the cost of utilities, raw materials and products, and the evaluation of operating cost of the plant. So first of all, you need to set up the complete flow diagram for the plant. Okay, then you need to define the cost of utilities like cold utility, hot utility, and different kinds of like raw materials and products. Then you need to evaluate the operating cost and you need to compare, because suppose you are using a heater, so you can provide heating by like electric heating, you can do like some kind of oil heating, you can do also use the steam for heating, and you can also use some kind of like biogas or CNG. So based on that, the cost will change. So you need to evaluate the best possible option for your plant. So these data were available in the case study, like the purchase price of isobutane, selling price of isobutane, selling price of hydrogen, cost of electricity, cost of natural gas, cost of furnace oil, and the cost of high pressure steam. So you have given the cost, so you can enter the cost in the Aspen and you can calculate. So for more detail regarding this case study, please refer the class notes and video. You will get to know more about this. So just let's start with the assignment questions. So which among the following is not a standard utility item in Aspen Plus? So you have options coal, electricity, steam, and wood. Because we have some standard utility items in Aspen, so you can directly use those standard utilities. So you have four options: coal, electricity, steam, and wood. Which one is not standard and not available in the Aspen Plus?
Wood.
Okay, so we have an answer wood. Anyone else?
Coal is also not a standard utility.
Okay, have you checked the Aspen software?
Yeah, I'm checking.
Okay, check. Because normally
Coal is listed.
if we are making a flow sheet for the thermal power plant, then I think coal will be there. So in my opinion, I think coal should be there. Maybe then direct coal name is not mentioned, maybe like in some other form, but I think coal should be there because coal is the main feedstock for a power plant. Okay, so the correct answer is wood. Okay, so you can go to the Aspen and you can check the utilities. So there, the wood is not an standard utility. So there is figure 19 is the utility results of an Aspen plus simulation run. Okay, answer the following 4 questions with accuracy up to 3 digits after decimal point. So the question number 1 is the most expensive among the available utilities: electricity, gas, steam, water. So in this figure, you can see the utility cost summary. So the figure is giving you a cost summary for utilities. You can find different kind of utilities here. You can see the name type. So this is the water, electricity, oil, steam, and gas. Okay. Then you have different kinds of parameters and you can see the results. So just check this figure carefully and let me know which one is the most expensive among the available utilities in figure 19.
Electricity.
Okay, so we have one option, one answer, option A, electricity. Anyone else? Okay, so what is your reasoning for option A, electricity?
The costing rate is highest. $63
So
per hour.
costing rate, so 63, you mean to say it's here. So
Yes.
costing rate, okay, dollar per hour, okay. But for the oil, it's 430.
It is not given in the option. So
Okay, so oil is not given an option, but you can see steam, there is nothing. Do you think the steam is free?
steam is not free, but I think it is not being used in the problem statement.
Okay, so it means then maybe you need to read the question again. What is the question? The most expensive among the available utilities. So what is the meaning of this costing rate? It is dollar per hour. Okay, so it means that you are using these utilities, but it is not mentioned in the question that the utilities is being used or not. The question is the most expensive among the available utilities. Which utility is the expensive? So I think you need to find a different parameter to assess the most expensive one, because this data, the costing rate, like as you said, that steam is not used. Yes, it's correct. I think the steam is not used. So we cannot compare it, okay, because we have not used it. And there is a reason, because maybe if we use it, it will be very costly. That's why we only compared water, electricity, and oil. Then how will you compare all the utilities? Then I think you need to find a different parameter. So I think you should check again figure 19. You will find an answer. Anybody else? Question is very simple. Just look. Is the figure clear to you or not? Are you able to see the figure clearly? Let me
Yes.
know if it is not visible clearly. I can read out.
Sir, I think steam will be the answer because its energy price is highest for steam.
Yeah, steam will
Yeah,
be higher. So 1 to
yeah,
1 2
nice.
point.
Yeah, nice, Manish. So this is the like parameter by which you can assess the expensive utilities. So here you can see we have two prices, energy price and electricity price. So the energy price, like for the water, is dollar per gigajoule, and for electricity it's dollar per kWh. So electricity is only 0.06. This is 0.35. Oil is 11.02, steam is 12.46, and the gas is 1.70. So this is the parameter by which you can compare the expensive one or cheap one. Okay, and this costing rate is giving you the results that you used in your system, and for your system this is the result. Okay, so this amount you are spending to run your system for 1 hour. Okay, so basically to fulfill your system's utility demand, like that is the cost, but it's not the price for the utility. The price for the utility is these two. Okay, so compare among these. So as you said, the steam is the highest one, so the correct answer would be steam. Yes, steam. Is it clear? Okay, if you have any doubt, let me know. So which among the following utilities has not been used in the simulation? Electricity, oil, steam, and water.
Electricity.
Okay. The question is which among the following utilities has not been used in the simulation? So we have one answer, electricity. Anybody else? Again, you need to check the parameter by which you can compare, and I think in the previous question we discussed about it. Try to correlate.
Sir, steam or gas?
Yes. So steam or gas is not used because, like as we discussed, so this costing rate is representing the amount you spend for 1 hour run of your system. So you can see only we have three data. Okay, we have data for water, electricity, and oil. So basically, in our simulation, we have only used these three utilities. There is no data for steam and gas. So these two have not been used. So check the options. So electricity is there. So electricity we have used. So option A is wrong. Then the oil. So oil we have data for oil also the costing rate. It is not so it is also used. Then the steam. So steam, yeah, we don't have any data for this. So it means that the steam is has not been used. Then the water. So yes, water is also used. So only option A, B, C, and D. Only option C, steam, has not been used in the simulation. And the gas also has not been used, but it is not in the option. So the option is
See.
C, steam.
Sir, we can also find the answer by looking at duty, right?
Yeah, you can also check with the duty. You can also check with the mass flow. So basically, these data, because if you don't have any mass flow, Okay, so it means because mass flow, the full electricity, there will be no mass flow, but the heat duty, it will be there. So heat duty is also an indicator, and the costing rate is also an indicator. And the other indicator, I think, no, I think only these two are the common indicator that will be there. Okay, because if you are using any utility, then there will be some costing. So you can either assess by the duty or by the costing rate.
Thank you.
Okay, so the next question is, the utility water is released at space degree centigrade.
35.
So we have an
35.
answer 35.
Yes, 35.
Yes, so it's direct. Okay, so you can see the outlet temperature. Okay, the inlet and the outlet temperature you can see here. It's 25 and 35. So the released means the outlet temperature. So the outlet temperature is 35. The answer is 35. Now the cost of utility water is. So what is the utility cost for water?
0.5 into 10 to the power minus 5
How much?
is 22.6
22.62.
dollars.
We have one answer, $22.6 per hour, and I think there was another answer regarding 1.5 10 to the power minus 5.
0.5 into 10 to the power minus 5
Okay, what is your reasoning behind this answer?
per cost of utility water
Your
is.
voice is not clear, so please try to speak louder.
Yes, sir, I'm confused between this because
Okay,
it is 1.5 into 10 to the power minus 5 is purchase price, and what is 22.6, it is the cost incurred by us while using in simulation.
okay. So if you have a confusion, so I think you should check the unit that the question asked. Then I think your confusion will be clear. So just check the unit. So they have asked in dollar per hour.
Okay, sir. Okay, got it. 22.619.
So if you compare the units, so you can see here it's dollar per kg. So it's a purchase price, but the cost of utility water is like dollar per hour in the costing rate that the system. So system using some water at this flow rate to fulfill this heat duty. So the cost will be this much, 22.6198. So now we have another question. The question is, ethylene reacts with benzene to form the desired product ethyl benzene, and there is a consecutive reaction that produces the undesirable product M-diethyl benzene, and a third reaction combines benzene and diethyl benzene to form a ethyl benzene. And you can see these three reactions. Okay, C2H4. So it's ethylene plus benzene. It's M-diethyl benzene. Okay, then it's again reacting. So then ethylene is again reacting with this diethyl benzene and producing D10H14. Okay, so you can see these three reactions and the rates are given here. You can see the rates also. So you have given the units. Then ethylene and benzene both at 350 Kelvin and 20 bar are fed into a CSTR reactor via control valves at flow rates of 0.1 and zero point 0.2 kilomole per second respectively. So you have given the flow rates. Both the valves operate with the pressure drop of 5 bar and follows a calculation type of adiabatic flash for specified outlet pressure. So you have given the conditions also for the valves. Then the valid phases are vapor liquid, you've given the valid phases. The outlet of the CSTR also passes through a control valve which operates with the pressure drop of 2 bar, and its calculation type is adiabatic flash for specified outlet pressure. But its valid phase is liquid only phase. So you've given the valid phase for this one also. The reactor has a volume of 60 meter cube and it operates at 400 Kelvin and 15 bar in liquid only phase. And the PSRK property method may be used. Then answer the following two questions with accuracy up to 3 digits. Ethylene feed is a mixture of vapor and liquid. True, false. So you have a question. Take 5 to 7 minutes. So open your Aspen. First, define the components. You have 3 components: ethylene, benzene. Okay, ethyl benzene. So more than 3 components: ethylene, benzene, ethyl benzene, and M-diethyl benzene. To define the components, you have given the property method PSRK. Define the property method, and you have given other conditions like we are using 2 types of valves, then we are using a CSTR. So try to model this and let me know the answer. Ethylene feed is a mixture of vapor and liquid. So model step by step, okay? Don't model the complete system in one go. Just first model, define the components, define the property method, then define the input streams to the valves. And I think after that only you will be able to know the ethylene feed. Is it vapor or liquid? So first only model up to, I think, up to the valve only. Don't connect the CSTR, just run the system, and I think you will be able to see the condition of the feed. Are you trying, guys? Anybody trying?
Yes, sir.
Okay.
The answer is false.
Okay, so we have one answer, false. Okay, so let's start. So let me share my screen so we can solve it and check the answer. So open your Aspen, then open a new simulation. Then here you define the component. So first the component it benzene, I think. Benzene. Then we have ethylene. Then we have ethylbenzene. So ethylbenzene you will not find directly, so you need to use the find command. Okay, click on find and type the name here. It is ethylbenzene. So type the name, click find now. I think I did some spelling mistake. So it's ETHYLENE, ethylene benzene. So ETHYL, only ethyl benzene.
If you just put the chemical formula in a component ID, then then also it will
Yeah. We can also do that, but I want to show you by typing the name. Okay. So you can say the name is ethyl benzene, not ethylene benzene. So ethyl benzene, you will find some compounds here with their formula. Okay. So then search the ethyl benzene. So here you can see the ethyl benzene. It's C8H10. So click on add selected compound. So you can see it is, you can see it here. Okay. Or you can also type the formula C8H10, then you can also find it. Then the second one is M-diethyl benzene. So the formula for this is C10H14. Okay. So now let's try with the formula C10H14. So you can see you have something C10H14. So now find M. So yes, M-diethyl benzene. Okay. So it's C10H14. So click on add. Then if you click on replace, then your previous added will be replaced, but no, we want this one also. So click on add. So you can see it is added here. Now we have all four components. Now click on next. Now here we define the method. So in the question, the PSRK property method may be used. So you need to define the property method as PSRK. So find the method. Okay, so it should be PSRK. So here it is. Okay. Predictive Redlich convent. So equation of state PSRK. Then click next and run the property simulation. Okay, so it's done. So the results are available. Now go to simulation environment. So here, if you read it, you can see the ethylene and benzene both at 350 Kelvin and 20 bar are fed into a CSTR via control valves at flow rates of 0.1 and 0.2. So basically, it means that there is one stream of ethylene and one stream of, you can say, benzene. Then there will be a wall, okay, and these walls are going from these walls. You can control the flow, and these two are going into a CSTR reactor. So first, because the question is ethylene feed is a mixture of vapor and liquid. So if we only design up to here only, so I think we can check the stream results at this pressure and temperature. So do this. So we have valves here. So V1 and V2. Okay. So we have two valves. Now connect the streams. So let's say stream S1. S2. Okay, so you've connected these. So click next. Now it's asking for the S1. So first stream is which one? What is the temperature?
77 degrees Celsius.
What is the temperature for stream S1? Suppose the stream is benzene. Anyone?
77 degrees Celsius.
Your sound is not clear. Okay. So the
77
temperature.
degrees.
Okay. So your voice is very down. Please check your mic. So you can see the temperature and pressure here. Okay. So both ethylene and benzene are at 350 Kelvin and 20 bar. You can also enter in degree or you can also enter in Kelvin. So let's enter in Kelvin, 350 Kelvin and 20 bar. So what is the flow rate? So flow rate is given here, like suppose first I am considering the ethylene, then the flow rate is 0.1 kilomole per second. So enter 0.1. Okay. So whenever you enter the flow rate, change the basis, like it's a molar flow rate, change it to mole. Select the appropriate unit, then select here fraction. Okay. Mole fraction. So the benzene, we are first selecting the ethylene. So the mole fraction of ethylene is 1. So basically the stream S1 will have only ethylene with this condition. There is no benzene and other components. So the mole fraction of ethylene will be 1. And click next. Now the stream S2. So S2 is also having same temperature, it's 350 Kelvin and 20 bar pressure. Okay. flow rate is mole flow rate, kilomole per second. The flow rate is 0.2 for benzene. 0.2 for benzene. So it's 0.2. Now the benzene will be here mole fraction, okay? Then benzene will be 1. So it means that the stream S2 have only benzene and nothing else. Both are defined. Click next. Now the valve B1 and B2. So valve for benzene and ethylene. So we have given that both the valves operate with pressure drop of 5 bar. So there is a 5 bar pressure drop, follows a calculation type of adiabatic flash for specified outlet pressure. And the valid phases are vapor and liquid. So you've given some conditions. So give this condition to valves. So vapor liquid, okay. You've given the pressure drop. So how much is the pressure drop?
5 bar.
5 bar. So what should I enter here?
5.
5 or minus 5?
Only 5.
Yes. So it's because it's directly written pressure drop. So we will enter 5. Okay. So this one is defining the pressure drop. And the type is the adiabatic flash for specified outlet pressure. Okay, it is given, I think, in the question. So the adiabatic flash for specified outlet pressure. So select these three. You can see the inputs are okay. It's blue and click next. Again, for the second valve, same pressure drop. Okay, click next. So all required input is complete. So now we can run the simulation. So click OK. So we have results. Now go to the stream results. So here we have stream. So the S1, S2, S3, and S4. So S1 is the benzene. Sorry, S1, which one is the S1? So S1 is this one. So S1 is the ethylene. S1 is the ethylene, S2 is the benzene. So here you can check the phase. So S1 is vapor phase and S2 is liquid phase. So ethylene is in vapor phase and the benzene is in liquid phase. Okay. So the question is about ethylene. So ethylene feed is a mixture of vapor and liquid. So from the Aspen, we can see the ethylene stream S1 is only on in vapor phase. Okay. So the given statement is false. So the correct answer is false. Any doubt? Okay. Now the temperature of the reactor outlet is. So now just also add the CSTR reactor, define the reaction kinetics, and let me know the temperature of the reactor outlet in degrees centigrade. So regarding the CSTR, define these reactions, your kinetics. You also given the volume. You've given the pressure, temperature, and liquid only phase. Any answer? Anybody? Is anyone trying? Is anybody trying? Let me know. Okay, so we can do this. So just go to the main flow sheet. Okay. Then we need to add a CSTR. So go to the reactors. You can find the CSTR. So click on it. Okay. So we have added a CSTR. Now we need to connect these two streams to the inlet to the CSTR. Okay. So right click then reconnect the destination. So it's here. Then for this one also, right click, then reconnect the destination. So it's here. So we have connected both streams. Then there is the outlet stream. So let's say it's stream S5. Okay. Now click on next. So click on next. Then it will ask you about the CSTR input. So we have given some data for CSTR. So the outlet of the CSTR also passes through a control valve, okay, which operates with the pressure drop of 2 bar. Okay, but it's valid phase, liquid only phase. The reactor has a volume of 60 meter cube, operates at 400 Kelvin and 15 bar in liquid only phase. So we have given the pressure, how much? It's 15 bar and 400 Kelvin temperature. So 15 bar is the pressure, 400 Kelvin is the temperature. Okay, the valid phase is liquid only phase. So liquid only phase, the valid phase. So change the liquid only. Okay, then the volume, it's 60 meter cube. So it's cubic meter, so 60 cubic meter. Okay, and now we need to add the kinetics. So kinetics, we need to add the reactions. So define a reaction R1. It is type of a kinetic power law reactions. Click OK. Then we need to go to the reactions, then R1. Then here we need to define the reaction. Okay. So the first reaction is ethylene reacts with the benzene. So ethylene, benzene, okay. Coefficient 1, 1. Then so they are making ethyl benzene. So it's ethyl benzene. Then we need to add another reaction. So the second reaction is the ethylene react with the ethyl benzene, and they are making diethyl benzene. So ethylene is reacting with the ethyl benzene, and they are making diethyl benzene. Now the third reaction is the benzene is reacting with the diethyl benzene, okay, and they are making 2-ethyl benzene. So benzene is reacting with the diethyl benzene, and they're making the ethyl benzene. Okay, C8H10. Okay, so we have defined the reactions. Now the kinetics. So you can see the equation here. We have not given any T0. Okay, there is no T0. The equation is like this. So if T0 is not specified, the kinetic factor is KT to the power n E minus E raised to the power minus E by RT. So compare these. So the value of K will be this constant. The value of K is for reaction 1 is 1.528 10 to the power 6. So it is 1.528 10 to the power minus 6. Okay, it's plus 6.
Plus
Yeah, thank you. So it is okay, and the n is 0 because you can see there is no t terms here, direct exponential. So and value of E is the, you can see we have given the unit here. The activation energy is in kilojoule per kilomole. So it is 71160. Okay. So the sign negative sign is already here. So don't include the sign negative. So kilojoule per kilomole, it's 71160, right?
yes.
Okay. So it's defined for reaction 1. Similarly for reaction 2. What is the K?
27780.
27780.
E is 83680.
83680 kilojoule per kilomole. Okay, for reaction 3, K
0.4167.
0.4167. K E
62760.
62760. So we have defined the reactions, so you can see it's done. So okay, we don't need to define anything else. So just click next, run the simulation. So results are available. Go to the result summary. Okay, so we need to find the temperature of the reactor outlet. So if we check our flow sheet, so the reactor outlet is connected to stream S5. The temperature of the S5 will be the temperature of the reactor outlet. Okay, so stream result,
126.
the temperature of S5 is, you can see here, the temperature 126.85. Okay, and the liquid phase, this is the temperature. So the answer should be 126.85. So is everyone getting the same answer?
Yes.
Okay, nice. So let's see the answer. So the answer is 126.83287. So our answer is correct. Okay, let's move. Is there any doubt?
No, sir.
Okay. Okay, so now we need to convert the simulation in pressure-driven dynamic mode. So now we need to convert this simulation into the pressure-driven dynamic mode. Choose a vertical CSTR of length 10 meter and a flat head. It operates on constant heat duty. The initial liquid volume fraction is 0.864. It models equipment heat capacity with mass 6800 kg and the specific heat capacity 500 joule per kg Kelvin. It includes a temperature controller. Save the Aspen Dynamics file and open it. Answer the following questions. So there is one point. So if you read the question carefully, the previous question, you need to connect a control valve in the after CSTR line. Okay. So before going to the dynamic simulation, just complete the simulation of the previous question complete. Okay. So just complete it first, then do the dynamic part.
Sir, how to do this?
No, first you need to complete the previous
Yeah,
question.
complete.
Okay, you completed?
Yes.
Okay. So have you not taken the last class?
No.
So okay. Okay, just wait for 2-3 minutes. I think okay, Manish, are you trying?
Yes, yes.
Okay, you are trying. So we have another one. Lakshmi.
Sir, I'm not trying actually.
Okay, are you also trying?
No, sir, no.
No. Okay. Okay, so if you both are not trying, then I think we can start the solution. So first, let's complete the previous one. So we have mentioned that the CSTR also passes through a control valve, which operates with a pressure drop of 2 bar, and its calculation type is adiabatic flash for specified outlet pressure. Okay, so just do that. So we need to connect again a control valve here. Okay, so reconnect this stream. So let's say it is stream S6. Okay. So we have connected this. Now click on next. So it's asking for the valve B4 input. So we have given the pressure drop of 2 bar, adiabatic flash, and the valid phase is liquid only. So valid phase, liquid only, pressure dropped 2 bar, and the adiabatic flash for specified outlet pressure. Click on next. So everything is okay. Now click OK. So your simulation is completed. Now we need to convert it to the dynamic mode. Okay. So for more info regarding this dynamic mode, you should refer the class notes and class video. So in that video, professor briefly discussed about the Aspen dynamics. Okay. So it's a totally different, you can say, a software. It's a part of Aspen. So like we are working with Aspen Plus, but it's a separate. Aspen Dynamic is a different part of Aspen. So it's also a complete uh, so many features. So you need to understand it thoroughly. You need separate classes. So but here we just discussed it very briefly. So you can refer the class notes, and if you are more interested in it, you can take some another course for the Aspen Dynamics. So now we need to convert this simulation into the Aspen Dynamic, because the Aspen Plus we do the simulation in static mode. Okay, so the all the conditions we are only considering the static. Okay, static mode we are doing on static mode. So now we are doing a dynamic mode. So we need to convert it. Okay, and you are given further conditions. So to convert into the dynamic mode, go to the Aspen. Then there is a, you can say, the dynamic here. So there is an option dynamic. Okay, so click on the dynamic mode. So when you click on the dynamic mode, then you can see, so required inputs incomplete. So you can see the inputs are incomplete. Okay, so if you see here, so you can see here, so this block is asking some input dynamic. So there is a new block. So there is a new option to enter the input for the block V3 in dynamic mode. So click on this. So it will asking some input. So you need to fill these inputs. So we have given choose a vertical CSTR, length 10 meter flat head. So vertical, type vertical, head type is flat head, length 10 meter. Then it operates at constant heat duty. So then the heat transfer, so constant heat duty. Okay. Then the initial condition we have given, the initial condition liquid volume fraction 0.864. So enter this 0.864. Then we have given it models equipment heat capacity with mass specific heat capacity. So mass is 6800 kg. So model equipment heat capacity, the mass is 6800 kg. You've given the heat capacity of 500 joule per kg Kelvin. So it's joule per kg Kelvin and it's 500. Okay. Then you have given it includes a temperature controller. So there's a temperature controller also. So click on the controller. So you need to select only the temperature controller. Include temperature controller. So now we have given all the given inputs into this dynamic mode. So now it's ready to run. So now click on run. So now simulation is complete. Okay, simulation is run. So now if you go to dynamics, then you can see these values are now. You can click on it. Okay. So the dynamic mode can be done by two, like the pressure driven and the flow driven. Okay. So it will be regarding the pressure driven. So click on the pressure driven. So when you click on the pressure driven, then it will ask you to save, like the save as type. So it will be a Aspen dynamic file. Okay. So as of now, we are working with the Aspen Plus. So the file version is the document file APWG. So first you should save this file. Okay. So like save as it's a compound file. So it is APWG. So let's say CSTR, save it. So now it's cstr.apwg file. When you click on the pressure driven, then it will again save in .dynf file. So then say rename it with dynamics. So suppose if anything happens, then you can open the previous file and you can start from this point. Okay, so switch dynamics, then click on save. So click on save button. So it will give you some error. Ignore these errors and it will open a new Aspen Dynamics file. You can see there is a pop-up. So close this one and open this one. So this is the Aspen Dynamics. So now you are in Aspen Dynamics. Okay. So now you are no longer in the Aspen Plus. So this is the Aspen Dynamics software. You can explore this. So if you see carefully, so this is our model, but you can see here there is another controller is here. Okay, you can see this controller B3TC. You can see so there is some kind of a temperature controller is here. So it is taking some input feedback and controlling the temperature of this CSTR. So it's a dynamic type of control. Okay, you can do so many things. You can read the manual and you can take some YouTube help. So now what is the question? The question is the controller is direct, true, false. So if you see here, we have a controller, okay, this one. So we need to check it, is it direct or in reverse? So if you click on it, then you can see the option like set point, the process variable, and the output. If you click on here, the configure, so you can see the condition of the controller. So you can see the controller action is reverse. Okay. So it is reverse. So the controller is direct, so it is reverse, so it is false. The correct answer is false. The controller is reverse. Okay. For more detail regarding this Aspen dynamic, please refer class notes. Now the next question is the default value of the gain of the controller. So there is a value of gain of controller. What is the default value? So if you again go to this window, then you can see the gain. So it is 5. So default value is 5. The answer is 5. So if you see the things, so this is the way we can control the things. Okay. So if you click on this run button, so it will run some steps. So you can see the set point is 126.85 and this variable was varying PV. So it's trying to reach the same. So you can see now they both are same. So after 2 hours, the steady state achieved. Okay, so you can see here initially it was unsteady state. After 2 hours, you can see the steady state is achieved. So here you can change the set point and it will try to achieve this condition. Just stop it. And if I suppose if I change the set point to 130, okay, and if I run it again, so now see this one is changing. So it is changing the parameter. It is trying to achieve go to the 130. So it's achieved like 130. So it is changing this output variable, and the unit is calorie per hour. So basically, it is changing the heat duty of the CSTR to achieve this set variable. So you can find the time, and after that there is a steady state. So this is the Aspen dynamics. So you can explore more about it. Okay. So let me stop it. So now again, the next question is, which among these is not an option for creating new utility? LP steam, hot oil, methane, and cooling water. Which among these is not an option for creating a new utility?
Methane.
Sorry,
Methane.
methane. Okay, we have one answer, methane. Yeah, so the answer is methane. So for new utility, we can not create using methane. LP steam, hot oil, and cooling water, we can create a new utility. Which among these is not an utility type? Gas, oil, coal, wood. I think we have already discussed it. It's wood. So now this is 4 figures. Okay. So the figure 1. In figure 1, you can see we have a main flow sheet. You can see the stream S3. Then there is a heater or cooler. Then the stream S2. Then the results for figure 3 heater, you can see the summary, outlet temperature, pressure, okay, all the details. Then there is the another figure, okay, it's figure 2, it's figure 3. So figure 2, you can see the utility inputs. So its type is the gas. Then you have the purchase price, you have the heating value, then this figure, then the results, okay. So you have 4 figure. Just take 2 minutes to go through this figure, then I will go to the questions. Try to understand these figures. What is the meaning of these? And what kind of value you can see here? And how can you relate them? Okay, so let's go to the question. The question number 1 is, So figure 1 is the relevant portion of main flow sheet of an Aspen plus simulation. Figure 2 is the data input palette of utility, which upon simulation run yields the result as indicated in figure 3 and 4. Okay, so 1 and 2 are the inputs, 3 and 4 are the results. Few results have been deleted in figure 4. In figure 4, next 5 questions are based on the figure 1 to 4. The temperature of stream S2 in degree centigrade. The question is the temperature of stream S2 in degree centigrade is. So see these figures and let me know the temperature of stream S2.
-43.9 degrees Celsius.
We have one answer 43.9.
9.
Yeah. So how do you know?
The outlet temperature, the outlet stream is S2,
Okay.
and the outlet temperature they have mentioned is 43.9.
Yeah, nice. So you can see here we have a heater. Okay. The input stream S3 and output is S2. So the outlet temperature of the heater will be the outlet temperature of stream S2. So we have the output results for the heater. So the output is the outlet temperature 43.9 from the heater. So it means that the S2 is at 43.9. So the answer should be 43.9. Your answer is correct. The pressure of stream S2 is in atmosphere. So the pressure of stream S2.
1 atm.
1 atmosphere.
Yes. So because it is again the same stream. Okay. So the outlet temperature will be the same. The pressure will be the same. So it is the 1 atmosphere from the outlet from the heater. So it will be for same for the stream S2. So the answer is 1 atm. The duty result at A in figure 4. The duty result at A in figure 4. So the figure 4 is this one. So the duty. So what is the result here?
5
Low.
kilowatt
How much?
of B1.
Please repeat your answer.
5 kilowatt
5 kilowatt.
B3.
Okay, so yeah, it seems correct because you can see the heater result. So you can see the heat duty is 5 kilowatt. Okay, so it means that we need the utility for 5 kilowatt. So the B3 heater duty is 5 kilowatt. Answer is 5 kilowatt. The usage result at B in figure 4. The usage result in at B in figure 4. So the usage, so what is the value for this?
So we have to simulate for this, or we just have to answer from these figures?
You have to answer from this figure only because you cannot simulate. You don't have all the data. So
Yes, the streams are
just
not.
use basic mathematics and basic thermodynamics. I think you will be able to answer. So just from units also, okay? Just see the units. So you need to find the uses, and the unit is in kg per hour, okay? And you have heat duty in kilowatt. Now to maintain that, to fulfill that heat duty, you need a utility. So you need to supply that. So how much of that kg per hour will you need? So just a simple calculation. You have given the heating value 50 megajoule per kg. So you have a particular gas, maybe it's 50 megajoule. It's methane. So you have methane. The LHV of methane is 50 megajoule per kg. Okay. Now from this 50 megajoule per kg, you want to have 5 kilowatt. So how much methane will you need kg per hour? Just find that, and that will be the answer. Are you getting my point? Is it clear, Manish?
Yes, sir.
Okay. So you can see here the heating value 50 megajoule per kg. We have heat duty 5 kilowatt.
0.36.
So how much?
0.36 kilogram per hour.
So we have one answer
Point-
0.36 kilogram per hour. So what is your reasoning?
Wait, the 15 megajoule per kilogram,
Okay.
and here it is 5 into 10 power minus 3 megajoule per second duty.
Okay.
So 5 into 10 power minus 3 divided by 50
Mm-hmm.
into 3600.
Yes. So you have given the heating value 50 megajoule. Okay. So let's say heating value. So it's 50,000 kilojoule per kg. Okay. You have heat duty 5 kilowatt. So you can say heat duty is 5 kilowatts, so 5 kilojoule per second. So to maintain this 5 kilojoule per second, you need to use this gas. Okay. So you can just divide this and you can find what should be the flow rate of this gas to maintain this heat duty. So just divide it. So 5 upon 50,000. It will give you kilojoule per second, okay, multiplied by kg per kilojoule. Okay. So this kilo will cancel out. So your answer will be in kg per second. But we have asked kg per hour, then you need to convert the second into hour. So multiply with 3600. Okay. So 1 hour it's 3600 seconds. Dot 1 hour. So the second will cancel out. Okay. So it will be kg per hour. Okay. So the answer will be, I think, how much the answer is? So it's
0.36.
0.36. Okay, so this is the way you will calculate the usage results. So basically, you have to calculate the flow of the gas required to maintain that heat duty. Now the cost result at C. So as you are using some utility, then you need to find the cost. So what will be the cost dollar per hour for this heat duty?
Two 0.216.
Okay, so and how we should calculate?
It's $0.6 per kilogram into 0.36 kilogram per hour.
Okay, so now you know the uses. Okay, so you know the usage rate in kg per hour, and you have the purchase price. So based on the price, so you need to spend $0.6 per kg for this gas, and the usage rate is 0.36 kg per hour. So multiply both, you will get the answer in dollars per hour. The answer will be that is
0.21.
0.21. Okay. Yeah. Now we have another question. So we have another now 4 figures. Figure 5, figure 6, figure 7, figure 8. So in figure 5, you have a flow sheet. There is a heater, like from the previous question. Then there is a column. Then you can see the B4 is red flag column. You can see some, it's asking about duty, usage, and cost. Then you have results for this red flag column, and you have the reboiler stage performance. So take 2 minutes to analyze these data, and then I will go to the questions. Okay. So the first question is the duty result at A. So figure 5 is the relevant portion of main flow sheet of an Aspen plus simulation. Figure 2 is the data input palette upon simulation, and the figure 6 and 7 are the results. So the question number 1 is the duty result at A in figure 6. What is this duty result?
minus kilowatt minus 69.0066.
So we have answer minus 69.006 kilowatt is the duty.
No.
So the answer is 88.82. Okay. Notes minus 66.
Okay, it's below.
Yeah.
It's very boiler. Summary.
So if you see carefully, so here it is asked about the reboiler duty. Okay. It's reboiler and duty for the
Okay.
reboiler. So the reboiler is bottom stage performance and this is the condenser top stage performance. So this heat duty is for the condenser. So
Condenser.
don't confuse. So this is question. It's very simple. You can see the duty. The trick was to see this condenser and the boiler, reboiler. Okay. So this is the question basically. So in the exam also, you may have same kind of question. So please don't make mistakes. So read the question carefully. So you have two. Okay, it's condenser heat duty and reboiler, and you have two in outputs. So this is for condenser and this one is for the reboiler. So this is the correct answer, 88.246. The next question is the user's result at B in figure 6. The user's result at B in figure 6.
Is cheaper.
The thing is that you need to consider the previous question cost, okay? So consider the same data, the 50 megajoule per kg, because we are using the same gas, okay, utility. 50 megajoule per kg, and this is the price, $0.6 per kg. Just note it down. So these are the values you need to use to calculate the uses and the cost. Any answer? Manish? Lakshmi?
So we have to 88.826 kilojoule per second multiplied by 50,000 kilojoule per kg. So is it 6.395 kg per hour?
Okay, let's see. Yes, so the answer is 6.39. So as we did in our previous question, so we have the heat duty, okay, and we have the CV. 50 point calorific value, 50 megajoule per kg. So divide these two, change the units. So you need to change it to kilojoule. So 50,000 kilojoule per kg. Then it's kilojoule per second. So divide 88.8246 divided by 50,000. You will get 0.001776,492 kg per second. But we have asked kg per hour. Then convert that into hours multiplied by 3600. You will get 6.3953 kg per hour is answer. Okay, so that will be the uses. It's 6.39. So this is the range. Your answer is correct. The cost result at C. So what is the cost? Now you have the flow rate, you have the price. For the previous question, the price in the previous question was 0.6 dollar per kg. So now let me know the price in dollar per hour.
3.837.
Just multiplied 6.39 with 0.6. So we'll get $3.837 per hour. So yes, the answer is this. Okay, nice. So thank you. So this is for today's class. Now we still have some time left. So Manish and Lakshmi, I want to hear from you. Like, what was your experience throughout these 12 weeks, and what is your learning from this course, and how will you apply these learning into your field? So Manish, maybe you can start.
Yes. So actually, I'm not working in process engineering field.
Okay.
I did engineering chemical technology in the year 2020, but right now I'm using in working in polymer industry in quality control department from 3 years.
Okay.
And simultaneously, I was working. I was preparing for one exam just 6, 7, 8 months ago. That's why after the completion of that exam, I just enrolled for this course. Actually, I enrolled this course when I was in final year also, but at that time I could not complete. But right now I have completed this course, and actually I started the regular classes from I think week 5 or 6, and
Okay.
attending the regular lectures from week 5, 6 also only. So after that, these online lectures are very much beneficial for me actually, because
Thank you.
only going through that recorded lectures of Prabir sir, that is too much helping, but this live lecture helps clearing doubt if because it is a software, na, so many things are
Yes,
hidden, and
yes.
we
Yeah.
we must have clear idea that where to go and where to see that tabs and all things. So that is also very much helping session. Also your session and one more session is also there. So both the sessions are very much helpful for me.
Okay.
And actually,
So
I joined that this course because I just wanted to switch my career from quality to process engineering. That's why I joined, because I already had a basic knowledge of chemical engineering in the engineering only. So if
okay.
that is possible, I will try after certification course to change the job.
Nice, nice. Thank you, Manish. Thank you for sharing your experience. So I think now you will use this software a lot, and maybe you will excel more in the software and change your field in future. Okay,
Yes,
thank
sir.
you. So yeah, what about you, Lakshmi?
Sir, actually, I'm working in oil and gas design. So we are using Aspen HYSYS.
Okay,
And so to improve my skills, I joined this course. And due to lack of time, uh, like I attended a few lectures, and your lecture was very much helpful because
thank you.
I'm not listening those lectures by the professor because I don't get time. But this evening, Sunday evening, 7 to 9 is a good time for me to attend your session.
Yeah,
So I'm
after office,
actually,
yeah.
yeah. And so, and also, like only in this session, I'm understanding certain things. But after this only, I have to go through those lectures given by the professor. So this Aspen HYSYS we are continuously using in our oil and gas design.
Okay, so you are in which company?
Actually, I'm in Tamil Nadu, Coimbatore, Cabin Engineering and Services Private Limited. So I'm a
Okay,
process engineer here.
okay. So now you are already working with Aspen HYSYS.
Yes.
Okay, okay,
So
okay. Nice.
we get the vapor pressure, and normally we use it to get the data sheet. And
Okay,
also we are doing Aspen EDR and all. I'm not using frequently, so I wanted to learn it.
okay. Nice. I think so. Now it will be very helpful with Aspen Plus also, maybe in your work.
Okay.
So, so all the best for exams. Thank you for sharing your experience.
Thank you.
And yeah, I wish you all the best. So, thank you.
Thank you.
Thank you so much.
Thank you. So, I still have 7 to 8 minutes left. So, I will wait if anybody joins. So, yeah. So, you can leave actually. This is from my end. So, if you want to leave, you can leave. Yeah. If you have any doubt, you
Sir,
can ask me any more
yeah.
doubt if you have. We have still some time left. Yeah, Manish.
Sir, you are into this. Means you are doing PhD, right?
Yeah, yeah.
So, means your future goal is to be in the teaching field only.
No, no, I have not decided it yet. So first I will try with R&D. I want to go in
Okay.
R&D. Yeah.
And sir, these live lectures are provided for all the courses available in NPTEL, because I have enrolled for 3, 4 courses, but I have enrolled in for examination only for this course.
Yeah, I think yes, yes, because I think for each NPTEL course they are having this live session.
Because I'm not getting any announcement for other 3 courses. Like I also enrolled
Okay.
for polymer reaction engineering. But
Okay, so if
the
you
thing
are
is that there I have not paid the examination fees.
No, it's not depend on the examination fees. If you are not receiving the links, then maybe some courses are not having live sessions, but most of the courses are having live sessions.
Okay, because
Or
this is the
maybe,
first course I'm seeing live lectures for.
or maybe those courses are having like some particular live sessions, not regularly, maybe like from 3 to 4 weeks. So, but nowadays, after this PMR initiative, so most of the course are having live sessions.
Okay.
Yeah. Any other doubt?
No, sir.
No, sir. Thank you, sir.
Yeah.
All the best for your career too, sir.
Yeah. Thank you. Thank you.
Okay.
Okay.
Thanks.
So all the best. Thank you. Thank you, everyone. Those who are not able to attend today. So maybe you will enjoy this video, and maybe you have enjoyed all the videos, past videos. So all the best for your exam. Thank you. Thank you, everyone. Bye bye.
Thank you, guys.
Thank you, sir.
Thank you.